In this video we discuss how to define a bearing surface. The concept was introduced in Lesson 205, which defines what a bearing support is and what role it plays. A bearing support works by exchanging normal compressive stresses between two or more surfaces. In order that these stresses can be transmitted efficiently, it is essential that the bearing support is stiff enough. The contact surface between one plate and another, or between a plate and a constraint block, can in general exert compressive stresses. Its stiffness, however, will generally vary from one point to another, exactly as a plate's deformation varies under a constant pressure. The bolt layout's bending, which the bearing support helps to absorb, is normally exerted by an initial surface, called the applied load footprint. This is generally the transverse section of a member. The bending is transferred from this initial surface to the bearing support thanks to the bending stiffness of the plate to which the bolt layout is connected. In order that this plate can successfully transfer the normal stresses involved, it must be sufficiently stiff. The plate's stiffness depends on its thickness and on the geometry of the connection. A plate will be stiff enough in all its points if it is thick enough. In this case, the bearing surface can be the entire surface of the plate to which the bolt layout is connected. A thin plate tends to bend easily, and only a small area of it in the neighborhood of the applied load footprint can fulfill the role required. We can improve its stiffness locally by adding stiffening plates to connect the plate to the member that causes the bending. If enough of these stiffening plates are used, then the entire surface of the plate, despite its thinness, can successfully transmit the normal stresses and can thus function properly. The normal compressive stresses needed to absorb the bending are pressures normal to the middle plane of the plate. They can be thought of as a load applied to it. The figure shows the forces exerted on the plate by the weld layouts and the pressure exerted by the bearing support. A model adopted by the most recent standards offers a very useful aid to understanding which part of the plate may act as a bearing support. In this approach, the surface of the applied load footprint is extended by a certain width around the edge, determined by the plate's thickness and by other parameters. In this model, the stiffness is required only in part of the plate, namely that obtained using this geometrical construction. In a cantilevered beam, the stiffness depends on the inverse of the cube of the beam's span. The shorter the beam, the greater its stiffness. The same consideration applies to the plate to which the bolts are connected. The cantilevered beam's span is comparable to the width to be added to the surface of the applied load footprint. This span depends directly on the thickness of the plate. When stiffening plates are present, the surface of the applied load footprint is not just that of the member's transverse section. It includes the contact surfaces of the stiffening plates as well. The figure shows two long stiffening plates connecting the column to the base plate. The adjacent white rectangles represent the welds. These issues must be considered when we define the bearing surface. The designer is responsible for specifying a realistic bearing surface. CSE provides the user with a full set of tools for defining it. It may be one of the coplanar faces in contact, perhaps with a suitable additional border, or it may be the result of any sequence of Boolean operations applied to surfaces of this type. CSE determines the extent of the portion to be considered in the neighborhood of an applied load footprint using the formula in Eurocode 3. Let's reflect for a moment about what can happen if the designer specifies the bearing surface incorrectly. For example, as the entire contact surface of a fairly thin plate without stiffeners. In this case, the entire contact surface needs to resist the compressive stresses. The nonlinear computation will say which part of the surface will be under compression, and therefore reacting, and which part will be under tension, and therefore not reacting. Here, the yellow area is the reacting part. When the plate's resistance is checked using the FEM model, however, the compressive stresses exerted by the bearing support will become normal pressure loads in the model of the plate, which will be bent. Note the unscaled forces corresponding to the normal pressure exerted on the plate, in turn in the compressed area of the bearing support, shown in yellow in the previous image. There will be a certain set of stresses on the compressed side of the plate, von Mises stresses, depending on the pressures on the bearing support, and of course on the plate's thickness and on the mesh used for the computation. If the plate is too thin, then it will be bent excessively and will not be able to bear the load. In this example, the welds are considered as clamps, magenta-colored dots. We can now see what would have happened if the bearing surface had been a smaller surface, consisting of the applied load footprint with a border added around it, as illustrated. The nonlinear computation would have given a different compressed area, typically closer to the welds. The reacting part in yellow is clearly not a rectangle, but T-shaped. This is how it compares to the previous situation. The part of the plate under compression is now smaller, and the von Mises stresses in it do not exceed the yield value. To sum up, if we choose a larger bearing surface than is realistic, then the plate will be under much greater stresses because the areas of normal pressure will be much larger than necessary. The next lesson discusses the constitutive law for the bearing support.